Your network is screaming, but you can't hear it. In the old days, we used hubs. Hubs are dumb. They take a packet and scream it out of every single port, creating a collision nightmare. It's shared bandwidth, zero intelligence, and a security disaster. But then, the switch arrived. The switch doesn't scream. It whispers exactly where it needs to. This is the difference between a crowded room where everyone is shouting and a private, high-speed conversation. If you want to build scalable systems, you need to understand the brain of the LAN. Let's strip back the plastic and look at the logic.
A hub is a dumb device. It receives data on one port and broadcasts it to everyone else. This creates collision domains and wastes bandwidth. A switch is different. It's a layer 2 device that understands where data needs to go. Instead of broadcasting, it uses Unicast, sending the packet only to the specific destination port. This is the difference between a megaphone and a private phone call.
To accomplish this mission smoothly, the switch relies on 3 key actions. Learn the MAC addresses of its environment, decide whether to transfer or flooding the data, and prevent network loops via the STP protocol.
A switch starts its life empty. No map, no directions. This is the MAC address learning phase. When device A sends its first frame, the switch looks at the header. It's not looking at where the frame is going yet. It's looking at where it came from. It grabs the source MAC address, let's say 00-AA, and looks at the physical port it arrived on, port 1. It immediately writes this down in its MAC address table, also known as the CAM table. If the address is already there, it refreshes the aging timer. If it's on a new port, it updates the entry. This is a living, breathing database that maps physical hardware to physical ports in real time. Without this table, the switch is just an expensive hub. Now, the switch has a job to do: delivery. It checks the destination MAC. Here, the logic branches into 3 paths. First, known unicast. If the destination is in the table, the switch creates a dedicated virtual circuit. It forwards the frame only to the target port. No one else sees it. This is unicast. Second, unknown unicast. If the destination isn't in the table, the switch doesn't drop the packet. It floods it. It sends the frame to every port except the one it came from, hoping the right device responds so it can finally learn its location. Third, broadcast. If the destination is FF:FF:FF:FF:FF:FF, the switch must flood it to everyone. This is how discovery protocols work, but it's also how networks get congested. The MAC table isn't infinite. It's a hardware-limited resource. Several things can break this logic. Aging is your first defense. If a device goes silent for 300 seconds, the switch flushes the entry to keep the table lean. But then there's table saturation. In a MAC flooding attack, a hacker blasts the switch with thousands of fake MAC addresses. The table overflows. When the table is full, the switch can't learn anymore. It reverts to fail open mode, acting like a hub and flooding everything. Your private data is now visible to everyone on the segment. Also, topology changes, like a link failing, can trigger a flush, forcing the switch to relearn the network from scratch to avoid sending data into a black hole. But there is a bigger boss in the background: Spanning Tree Protocol, or STP. In professional networks, we want redundancy. We connect switches in loops, so if one cable fails, another takes over. But loops are deadly for layer 2. Without STP, a single broadcast packet would circle the loop forever, duplicating itself until it creates a broadcast storm that freezes the entire network. STP prevents this by electing a root bridge, the king of the network. It calculates the shortest path to the root and then logically blocks redundant ports. These ports stay orange or blocked. They don't forward data, but they listen. The moment a primary link dies, STP unblocks the backup port in milliseconds. It's the invisible hand that keeps the network loop-free and alive.
Ethernet switching is the foundation of every data center on the planet.
From simple Mac learning to the complex failovers of spanning tree, these mechanisms are why your video calls don't lag and your transfers stay private. Want to master the full stack from layer 2 to the cloud? You're in the right place. Follow Beta Growth Tech for more system design explained fast. Save this for your next network engineering interview. Drop a switch in the comments if you've ever had to troubleshoot a broadcast storm.